The next speaker is a former member of the Harvard Economics Department, currently at Stanford, Guido Imbens. And in the world of econometricians, he's one of the few we think it'll be useful to listen to. Many of our econometricians, many of our econometricians are very technocratic with very little ideas. And when Guido came to our department as assistant professor, his ideas already seemed interesting, although he tells me that his PhD was one of the papers he would withdraw at this point because his thinking has gotten so much advanced.
Thanks. Thanks very much. So I'm not sure whether that's just setting a very low standard by saying that by compared to other econometricians. But thanks for the invitation. This is joint work with Susan Athey and Dean Eccles. So Susan was here Monday, Tuesday. She left yesterday, so I could get here in time, and there's still be somebody at home. Dean Eccles was at Facebook till this summer, and he just moved to MIT. And so this is some work that most of it was done kind of last summer a lot of it last summer when I was visiting Facebook and kind of looking at some of the statistical problems they were thinking about there. One of the advantages of having moved from Harvard to Stanford has been the proximity to the tech companies and kind of seeing what kind of statistical questions they have there. So here, what we're interested in is looking at spillovers in networks. And so the setting, although we don't at the moment have the application that we're working on, because there's some issues with the data, but we're thinking about Facebook-type settings where there's a very large connected network, and we're interested in the causal effects of interventions there in the network. We're interested in seeing what happens if we expose a particular individual to some treatment or some intervention, and we think that that may not just affect their outcomes, but it may also affect outcomes of the people they're connected to, and possibly beyond that, it may affect people they're not even connected to, but who are linked to them through others. And so in many cases, what we do, so that problem would be much easier if you had a whole bunch of disconnected networks. If you just had a large number of networks, and so that type of situation may arise if you're looking at educational data where we think the spillovers are confined to classrooms or to schools. And so if you had a lot of schools where individuals in different schools didn't interact with each other, we could just look separately at the schools and kind of treat the schools as the units of analysis. That doesn't directly work in the Facebook type setting because there's one big network and in the end everything is connected. Now in practice, that is still what a lot of people do. And so when Facebook does experiments kind of on interventions where they expect these spillovers to be big, they often just partition the whole graph into a number of subgraphs that are less well connected. They're still connected, but they just ignore those links. So they may try out an intervention in New Zealand because people from New Zealand don't tend to be very connected to the rest of the world. So if you kind of that way partition the graph into a bunch of graphs and ignore these spillovers, you can make some progress. Here we want to not make that type of approximation. We want to keep the network intact and see what we can learn in the context of a single connected network about these spillovers. And so very specifically, we're going to look at tests for particular configurations of these spillovers where we'll try to calculate exact p-values, so not relying on asymptotic approximations where the network has to get bigger or become somehow less connected. And I'll sort of make some comments at some point that this is not necessarily the ultimate goal of this research project. Just doing the testing isn't all that interesting in its own right, but it shows you that where the information is in the data without making assumptions about the structure on the network. So here's a roadmap. I'll talk a little bit about causal effects in general and potential outcomes. Talk a little bit about Fisher exact p-values, and then I'll talk about what we are proposing to do for the type of null hypothesis we're interested in. But so what we're interested in testing relatively complex hypotheses on causal effects in a setting where we have a single network and individuals may all be connected through that network, and the null hypothesis we're interested in put structure on the spillovers that are allowed. And so one of the motivations is a paper by Bond, Ferris, Jones, Kramer, Marlowe, Settle, and Fowler, where they around the 2008 election, they did this. Sorry, the 2012 election, they did this experiment where they changed the Facebook page of a bunch of individuals so that you could see and show that you had voted. And so for some of your friends, or some of your friends could see that you had voted, and the question was whether that would affect other people. And so it's very plausible that seeing that you voted affected your friends, and it's sort of very clear that it did. But in the paper, they claim more than that. It claimed that not only did me showing that I voted, or giving me the option to show that I voted, affect the voting behavior of my friends, but they claimed that it also affected the voting behavior of friends of my friends who could not possibly have seen the message on my Facebook page because they didn't have access to that, but because my friends voted more as a result, that there were actually detectable effects on friends of my friends. And similarly, in a paper that received a lot of attention, Christakis and Fowler, where they look at the spread of obesity in a network, they claimed that if I gain weight, that has a causal effect on the weight of my friends and relatives, but beyond that, it also has an effect ultimately on the friends of my friends. And so the question is how we can formally test such claims without putting structure on the network, and allowing for the possibility that the network has formed in a way that people with similar tastes in food may be connected, so that it's very likely that that weight is correlated in the network to begin with. And so ultimately, we're trying to get the data for the Fowler et al. Paper and apply some of these methods there, but there were some issues there with the data, and Facebook has since then also gotten burned a couple of times by some of the data that got out, so that it's a little harder to make that work. But so the first point I want to make is that clearly there's some evidence in the data about spillovers that is separate from any structure on the network. Suppose we randomly assign the treatment, sort of binary treatment. And suppose we have two individuals, both who are in the control group, so neither of them were exposed to the treatment, both with a single friend, where for one of these two individuals the friend was treated and the other one, the friend was in the control group. Then at that point, if we find a correlation between the individuals for the egos, so for these first two individuals and the treatment for the elders, then that would be evidence of spillover. So if we find a lot of individuals in the control group who had a single friend, and we then compare the average outcomes for those individuals with the treated friend, and the individuals with a friend in the control group, that would be evidence of spillovers without relying on assumptions about the structure of the network. And so what we want to do is construct tests based on that type of comparison, so that if the network is sufficiently large, we can make precise statements about the p-values of those hypotheses. So now let me discuss the setup for a little bit. And so here, the way I want to think about causal effects is in terms of potential outcomes, but specifically the work associated with the research by Don Rubin here in the stats department. And so I want to set things up with a finite population. We have n units. These units may be linked through an arbitrary network with adjacency matrix G. And we expose some of these individuals to various levels of the treatment. Most of the time, I'm going to look at a case where we just have a binary treatment. So each individual is either exposed or not exposed to the treatment. So in the Facebook example, either I have the option of posting about my voting behavior or not. And we're going to assume that that treatment is randomly assigned at the individual level. Now, for each unit, for each of these n units, there's a set of potential outcomes denoted here by yi of w, one potential outcome for each level of the treatment. And here, in principle, at this moment, I'm allowing the outcome for individual I to be a function to depend on the treatments for all n individuals. And so the key thing is that it's not restricted to be a function only of the treatment for that individual. It can depend on treatments for any other individual as well. And causal effects here are simply comparisons of these potential outcomes. And so what Paul Holland called the fundamental problem of causal inference is that we can't ever see both of these terms. We can see yiw for one particular value of w, namely for the treatment that was actually assigned, but we can never observe it for any other treatment. And so somehow we have to impute these missing potential outcomes to get estimates of the causal effects. And we'll exploit the fact, we're going to heavily exploit the fact that these treatments are randomly assigned in order to do so. And so in most of the literature, people have made what Rubin called the stable unit treatment value assumption, or SUTVA, that these potential outcomes depend only on the own treatment. And in that case, things are very simple. If we have a randomized experiment, we can simply compare average outcomes for treated units with average outcomes for control units, and that gives us an estimate of the average causal effect of the treatment. But now, without that assumption, there's certainly lots of causal effects we may be interested in. If I'm an individual who is connected to 5 other individuals in this particular network, there may be treatments associated with, there may be outcomes associated with various of my friends being treated. It may depend both on the number of friends who are treated. It may depend on which of these friends got treated. It may depend on their friends getting treated. And so there's in principle lots of things we could try to estimate. Here, we focus on a much simpler question. We're going to just look at exact tests, whether particular types of spillovers are present, and whether we can learn about them in the context of data just on the outcomes, the treatments, and the network structure. And as I said in the introduction, ultimately just these tests are not all that interesting. Just knowing that a particular intervention has some effect may not be all that helpful for implementing an optimal policy, but it's a starting point, and it shows that the randomization allows you to detect these effects, and that'll be the first step to actually estimating particular averages corresponding to policies. So in the Facebook case, what they would often be interested in is if a particular, they would be interested in what the effect would be on outcome, say, measured through user engagement at the website, if they make a new feature of the website available to everybody. They want to estimate that by making it available to only a subset of individuals. And the complication is that these effects may depend on how many and which of your friends are actually treated. For example, if the new feature is some Skype type tool that allows you to interact with your friends in a different way, then clearly that can only have effects if some of your friends have that tool as well, and and their uses of the new feature may depend on how many of their friends have that feature, and so on. So that getting estimates of the overall effect gets very complicated if only few people have it in the experimental phase. So now let's look at the second component of what we're doing, these Fisher exact p-values. And so let's focus initially in the case where there's no interactions at all, where we maintain a stable unit treatment value assumption. So now there's only two potential outcomes for each unit, y0, y1, depending on whether the unit was in the control group or in the treatment group. I suppose we're interested in testing the null hypothesis that there's no effect of the treatment whatsoever. Then if we keep the population fixed, the n units in the population fixed, we keep their potential outcomes fixed. If we look at a statistic like the one here, the average difference, the difference in average outcomes for the treated minus the average outcomes for the controls, we can figure out the exact distribution of that statistic under the randomization distribution, under the distribution generated by randomly assigning half the individuals to the treatment and half the individuals to the control group. We can infer that exact distribution because under the null, we can infer all the missing potential outcomes. We only see y0 for the control units, only see y1 for the treated units. But given that the null says there is no effect, we can infer what y1 is for the control units and what y0 is for the treated units. And we can get the exact distribution of that statistic without making any distributional assumptions on the potential outcomes. And so what we would do is, given the statistic, we would calculate the p-value as the tail probability associated with the observed value of the statistic. We calculate the exact probability under that randomization distribution that the statistic is in absolute value greater than or equal to the absolute value of the observed statistic. Now, I'm saying that we can calculate these exact p-values. In practice, of course, we can't actually do that if n is fairly large, because there would be too many possible values for the treatment assignment. But we can approximate that arbitrarily well and very fast, and without relying on distributional assumptions of the type we would like to avoid here. Now, this type of inference sort of has a long tradition. It goes back to Fisher, and it's still sort of essentially at the basis of all the testing for effects in clinical drug trials. There's some controversy about these methods in various parts of the literature, but I want to sort of take that here as given and exploit the fact that it's just gives you very clean inferential results that don't rely on assumptions on the network that some people in this literature have made as a way of making inferences on spillover effects. Now, what are the hypotheses that we're interested in here? So the simplest one, and the one for which there's no need to do anything very complicated, is just that there's no effect of the treatment whatsoever. In that case, the null hypothesis is sharp. We can infer all the potential outcomes from the observed ones, and we can directly calculate the exact p-values or large sample, approximate them arbitrarily accurately. But that's not a very interesting assumption, because under that assumption that implies the stable unit treatment value assumption. We're back in the case we understand well. A more interesting hypothesis is that there's no effects on friends of your treatment, but there is effects. There's own effects of the treatment. So maybe that exposing you to an intervention affects your outcome, but it doesn't. But exposing your friends to the treatment doesn't affect your outcome. And so here, what we want to test is just whether there's any evidence of spillover effects. Beyond that, we may be interested in assumptions about higher order effects. I gave this quote from the Fowler et al. Paper that where they claimed that there were effects not just of the friends being treated, but they claimed there were effects going beyond that. There were effects of friends being treated on your outcomes. And so that's a null hypothesis we want to consider, where we're allowing for unrestricted effects of your own exposure to the treatment. We're allowing for unrestricted effects of your friends being exposed to the treatment. And we're interested in testing whether, given those effects, there's any evidence that treating friends of your friends has any evidence on has any effect on your outcome. And we can go beyond that, looking at third order effects. At that point, power is going to be a big problem. We can also look at other null hypotheses in the same spirit. We can look at the hypothesis that it's only the number of your friends that is treated that matters, and it doesn't actually matter which of your friends get treated. Alternatively, it may be that if well-connected friends of yours are treated, that may have a bigger effect than treating less well-connected friends of your friends. We may also be interested in testing whether sparsification of a network is valid. We may have a big network where individuals have lots of friends, but we may want to test whether a sparsification of that network, where we only count as friends people you interact with on a fairly regular basis, is valid in the sense that spillover effects only works through these close friends rather than through all the friends. But so in all cases, the problem is that these null hypotheses are no longer sharp. They're no longer sharp in the sense that given the observed outcomes, we cannot infer what all the values are for the missing potential outcomes. If I was exposed to the treatment, I cannot infer under the hypothesis of no spillover effects, I cannot infer what my outcome would have been had I not been treated. I can infer what my outcome would have been had my friend's treatment been changed, but my treatment kept the same, but I can't infer the outcomes for me given a different level of my own treatment. And so the problem is going to be that for these more interesting hypotheses, the null hypotheses are no longer sharp, that we can't infer the exact values of all the missing potential outcomes. And so the standard Fisher approach relies very heavily on that. It looks at all possible assignments and looks at the value of the statistic in that distribution. We can't do that here because for some values of the assignment, we can't infer the corresponding value of the statistic. So what have people done in the literature? So in the Fowler et al. Paper, Fowler et al. Paper, they look at a statistic that averages ego outcomes over all friendships with treated alters, and then subtract the average of ego outcomes over all friendships where the alter was in the control group. And then they calculate exact p-values, but not under the null hypothesis that there's no treatment that allows for own treatment effects, but they calculate the p-values as if the null hypothesis is that there's no effect of the treatment whatsoever. And so these p-values aren't necessarily valid if, in fact, there are own treatment effects. And there's sort of some theoretical calculations in the paper that show that the rejection rate under the null, if we do a 5% test, can be as large as 20%, depending on what the configuration of the data is. But the point is just that this test is not valid because it doesn't allow us to calculate all the potential outcome, all the values for the test statistic under the null that we're actually interested in of no spillovers. And so what do we do? And so the key conceptual contribution of the paper is that we analyze a different experiment from the one that was actually performed. So what is the experiment that was performed here? We had n units. We randomly selected some subset of them to be exposed to the treatment and assigned the others to the control group. We can't calculate the p-values for null hypothesis of the type we're looking at, of no spillovers for that experiment, because we don't know all the missing potential outcomes that go into that statistic. And so what we do is we look at a different experiment that is implied by the experiment that was actually carried out, but that makes the null hypothesis of interest sharp for that artificial experiment. And so how do we do that? There's sort of two steps in defining that artificial experiment. The key first step is that we take a subset of the whole population, and we call these the focal units. And we're only going to use outcome data for these focal units. So we may have 10 individuals in the population. We're only going to look at outcomes for the first 2 units in that population. And then we're going to figure out, if we only look at these 10 units, we're going to look at which treatments would not change the outcomes for those 2 units under the null hypothesis. And so under the null hypothesis that there's no spillovers, we can change the treatments for the other 8 units. Because the hypothesis that there's no spillover says changing the treatments for these other 8 units is not going to change the outcomes for these 2 units, these first 2 units. And so we're going to look at the treatments that keep fixed the treatments for the first 2 units, but change the treatments for the other 8 units, and look at the outcomes for these first 2 units. And now we're back in a situation where the hypothesis of no spillovers is going to be sharp for that artificial experiment, and we can figure out the exact p-value for that for a statistic that depends only on the outcomes for these first 2 focal units. So the terminology here is that we take this subset of units, and in principle we can take an arbitrary subset of the original population. How we choose that subset is going to affect the power substantially of the test, and we have some thoughts on that. But for the validity, it doesn't matter how we choose these focal units. Then, in the case of no spillovers, we're going to treat all the other units as what we call auxiliary units. We're going to look at the randomization distribution, where we change the treatments for these auxiliary units, keeping fixed the treatments for the focal units, and look at the outcomes for the focal units. And then any statistic defined on the outcomes for these focal units is going to have a randomization distribution that we can infer exactly under the original experiment. And so here, if we have a set of focal units, for each of these focal units, we look at which set of treatments would not affect their outcomes. We take the intersection over all focal units. Sorry, it says here the union, this should be the intersection. And then we can figure out the randomization distribution for statistics defined on outcomes for the focal units over the assignments for these auxiliary units. So this is essentially what I said here. So here, kind of to illustrate this, suppose we have a network here, sort of a small world type network. We choose at this point arbitrarily a number of units to be the focal units. We're going to look at only at statistics that depend on outcomes for these focal units. All the non-focal units are auxiliary units. We're going to look at the randomization distribution induced by varying the treatments for these auxiliary units, and then looking at the distribution of the statistic. Now, if we do this for the null hypothesis of no second order hypothesis, things get more complicated. Now we have three types of units. We have focal units whose outcomes we're going to look at. Then we need to keep fixed both the treatments for the focal units as well as the friends of the focal units, because friends of focal units would still affect treatment. Changes in the treatment for friends of focal units would still change the outcomes for the focal units in ways that are not restricted by the null hypothesis. So we can't change their treatments either. But units who are neither focal nor friends of focal units would not affect outcomes for focal units. And so we can change treatments for those units. So in this case, the red units are the focal units. Friends of these focal units are what are called buffer units. We keep their treatments fixed as well. And the remainder are the auxiliary units whose treatments we vary over through the randomization distribution, generating the distribution on the statistic, on any statistic that depends on the outcomes for the focal units. So what could we look at here? So if we look at the simplest case where we're interested in the presence of spillovers, we would modify the statistic that Fowler and Bondaral looked at, and now we would average over all friendships, so over all the pairs of individuals that are linked in the network. We would look at the average outcome for focal units. We would look at all pairs we would look at all friendship pairs where one of the units is focal, one of the units is auxiliary. We look at the outcome for the focal unit and average that over the friendships where the auxiliary unit was treated, and subtract the average of outcomes for focal units over friendships where the auxiliary unit was in the control group. So now we're no longer averaging over all friendships, we're only averaging over friendships where one of the units is focal, one of the units is auxiliary, and in the first term the auxiliary unit was treated, and the second average the auxiliary unit was in the control group. And now we get a statistic whose exact distribution we can infer given the randomization, and we can get an exact p-value for that for the null hypothesis. Now, it turns out that isn't necessarily a very good choice of statistic. More powerful. We look at some other statistics that may be more powerful based on linear models for spillovers of the type that Mansky has worked on in the econometrics literature. And so that motivates a particular statistic that's given here. I don't want to go into the details of that, but it turns out that even though the validity of the test doesn't depend on that linear model, if that linear model is a reasonable approximation, that gives us a test statistic that has more power against the alternative hypothesis, where there's an additive effect of friends being treated. Now let me show some results from some of the simulations we did here. And to make this realistic, we took a network from the EdHealth data set where we have a network of friends within a particular high school. There's about 600 individuals. We simulated outcome data that were normally distributed, and we allowed for a direct effect. And when we look at the power of the test, we allow for spillover effects of the friends. And so here's what that network looks like. And sort of for a particular set of choices of who's focal and by implication who's auxiliary, we look at the distribution of the test statistic under various configurations of that model. Here for the same data set, when we look at the testing the null of no second order spillovers, here's a configuration of what the focal, auxiliary, and buffer units look like. And so what these simulations show is that we get actually substantial power against alternatives where there are spillovers present. We assessed the importance of how we chose the focal units there. The simplest way obviously is to choose these focal units randomly, but it's clear that that's not optimal. You would like to make sure that there's a lot of friendships between focal units and auxiliary units, and so we used two methods that try to do better. One based on epsilon nets, where we start by randomly choosing some focal units, but then choose focal units who were not friends with any of the existing focal units. And the last method, we try to maximize the total number of friendships between we choose the focal units in order to maximize the total number of friendships between focal and auxiliary units to maximize power. Doing that directly is computationally very hard, so we do it in a greedy way where we start randomly and then each time choose the next unit to be focal who has the most friends who could be auxiliary units. And we see that choosing the focal units in a better than random leads to a substantial increase in power. We also looked at testing for second order spillovers, and there again we find that we can actually do this in practice for realistic size networks, that there is power to detect these effects, and so as a result we think that there's promise for actually trying to estimate these second order effects in these type of settings. As I said, we don't quite have the application on the Facebook data yet, but it does look like that there is going to be evidence of these higher order spillovers in these experimental settings. So 12:15 was the with. Okay, so let me then look at take a couple more minutes. So here we do have one other application from a data set that was originally calculated by Bruce Sassadot. There, it's a very simple network where, in fact, we have a whole bunch of pairs. He looked at individuals who are roommates, and he was interested in the causal effect of roommates being high-performing academically on the own students' performance. And so the question here is whether there's any evidence of being assigned a roommate who did well in high school on the individual's own academic performance. And so here it's sort of very easy to see how you should assign the focal how you choose the focal units. It's not a connected network, there's just a number of pairs. So in each pair, we want to assign one of the individuals to be focal and the other to be auxiliary. And then we look at the average outcome for the focal individuals with high-performing roommates versus the focal units with low-performing roommates. And so if we do that for a particular way of randomly selecting one individual in each pair to be focal, we do find that for the score type statistic, the p-value is actually is below 0.05, though for another statistic, it's closer to 0.1. So it looks like there's some weak but not particularly compelling evidence that these spillovers matter. Now, in that particular setting, this is Dartmouth roommates, so all these roommates are fairly high performing to begin with. So you wouldn't necessarily expect these effects to be huge, but there's some effect at least of spillovers on individuals' outcomes depending on their roommates. Okay, thanks.